Welcome to qnawire.
Hey everybody, today we'll be solving problem 79 from chapter 12, section 6. Chapter 12 is fluid mechanics, section 6 is viscosity and turbulence. Now, although this problem is out of section 6, I believe that we'll have to use a lot of concepts from section 5, where we deal with volume flow rates and just flow rates in general in order to solve this problem. So don't be deceived by the section 6 classification. The problem reads that you hold a hose at waist height and spray water horizontally with it. So we're just going to draw that basic system here on kind of like an XY graph. So somebody is holding a water hose at waist height. This is my little drawing of a water hose. And water is splashing out of it kind of in this manner, following the dotted line. And they're saying that the hose nozzle has a diameter of 1.80 centimeters. So we'll just write that down. And the water splashes to the ground at a distance of 0.950 meters away. Now remember that we have to write down the 0 even after the 5, because when we do the computations, this means that we have to keep track of 3 significant figures when it comes to our calculations as well as our answers. Now, this problem says if you constrict the nozzle to a diameter of 0.750 centimeters, how far from the nozzle horizontally will the water travel before it hits the ground? Now, what will happen when we constrict the nozzle is that the water is going to come out at a different velocity, and what we know already is that it's going to come out at a higher velocity. Now, how do we know that now the equation that describes this rule that water is going to come out at a higher velocity if the diameter of the nozzle gets constricted is something called the continuity equation, which means that the rate flow of volume of water in a hose is going to be equal to it's not going to be equal to, it's just going to be constant. So what it says is dv dt, where v is big V, which denotes volume, is going to be equal to A1 V1, which is also going to be equal to A2 V2, where A is the cross-sectional area of a hose, and then V is the speed of water in that hose. I'll write water as H2O. Now, in this problem, we can definitely compute A1 and A2, but we cannot compute V1 or V2. So this means that we'll only be able to establish a relationship between V1 and V2. So I'm going to rewrite the above equation in a manner that basically establishes a relationship in terms of ratios between velocities and areas. So V1 over V2 is going to equal to A2 over A1. And so for now, let's just find this ratio of velocities by doing calculation on the areas, on the cross-sectional areas of the hose. Now, we know that the diameter of the first hose is going to be 1.80 centimeters, which means that the radius is going to be 1.80 centimeters divided by 2. Make sure you keep track of your units and write them right after your numbers. So 1.80 is going to be divided by 2 is going to be equal to 0.900 centimeters. Now, notice how I wrote 2 zeros after the 9. That's to keep track of significant figures. Remember, there's 3 significant figures, so in this situation we'll have 9, which is 1 significant figure, and then the zeros make up the other 2. And another thing that I wanted to point out here is that in order to keep track of our units and make sure everything fits together, we need to convert centimeters to meters, which means that it's basically, and the reason why we do this is because of standard international notation and the fact that we're giving our distances that the water travels in meters. Now, the standard international notation for distance is meters. So instead of converting meters that the water travels horizontally to centimeters, it's actually best for us to convert centimeters to meters. Now, the way we do that is we use stoichiometry. And so this is how we'll be able to do that. Notice how centimeters as units cancel out at the top and the bottom. And the answer to this conversion problem is going to be that radius 1 is equal to 0.009 meters. Now, we'll compute A1, which is the cross-sectional area of our initial hose before its diameter gets constricted, which is going to be equal to pi r1 squared, which is equal to pi 0.009 meters squared. Now let's do that computation really quickly. That's going to be 2.54 times 10 to the negative 4th meters squared. And now let's do the same computation for the other diameter that we're given. Now, the constricted diameter, which we'll be calling D2 here, is 0.750 centimeters. Now, if we were to compute the radius, it'll just be 0.750 over 2. And then let's just do that. And then 0.75 over 2 is going to equal to 0.375 centimeters. And then finally, we have to convert 0.375 centimeters into meters. Notice again, the units cancel out, and we'll have radius 2 at 0.00375 0. Don't forget the other 0 for significant figure purposes. Meters. And then let's really quickly compute A2. Now, A2 is going to equal to pi times R2 squared. This means that it's going to be pi times 0.00350 squared. Let's do that computation really quickly. And then our answer is going to be 3.84 times 10 to the negative 5 meters squared. So, okay, we have A1 and then we have A2. Let me just underline the A. Let me just do a little circle on A2 and then D2. And then we have D1 and A1 underlined in red. Now, what we have to do is use these ratios of cross-sectional areas to find the velocities of water using the continuity equation. So just in a moment, we'll be able to switch our slides and come back to our continuity equation. Now, remember that the way we've written down the continuity equation at this point is rearranging it to represent velocities on one side and cross-sectional areas on the other. And it's also very important for you guys to recognize that in this situation, the designators for each variable are flipped. So it's not, make sure you keep track of that. Don't mess up A1 and A2. Now, A1 was 2.54 times 10 to the negative 4. And then A2 was 3.84 4 times 10 to the negative 5. And don't forget to make sure you include meters squared at the end of each one of them. And then let's do that calculation really quickly. Which is going to be 0.151. Now, notice that the meters in this situation cancel out. So this is a dimensionless quantity, as ratios should be. So what do we do with this information now? And what we do with it is actually apply it to a kinematics problem. Now, if you think back to kinematics and to projectile motion specifically, there's a law that you can derive that describes just this scenario that we're experiencing with water. And the scenario is, if you only change velocity, the horizontal velocity with which a projectile gets launched, and you don't alter anything else, you'll be able to use a special equation to solve this problem. And the special equation ends up being L1 over V1 is going to equal to L2 over V2. So in this situation, we do know what L1 is. We do not know what L2 is. And we already know the ratio between V1 and V2. So let's try rewriting this equation in terms of the ratio we've already come to derive. So first, we'll multiply both sides by V1. That's going to make V1s cancel on the left. And let's divide each side by L2. That's going to make L2s cancel on the right. So in this situation, we have L1 over L2 is going to be equal to V1 over V2. Now we know that that ratio is going to be equal to 0.151, and all we have to do now is just plug in for L1 0.950 meters. So let's go ahead and do that on the next slide. 0.950 meters divided by L2, which is what we're trying to find, is going to equal to 0.151. In this situation, what we'll do now is just multiply both sides by L2, and then divide both sides by 0.51. 0.151. And so in this situation, L2s cancel here, and we'll 0.151 cancel on the right. And so we have one last problem to do on the left to figure out what L2 is. 0.950 divided by 0.151 is going to be equal to 6.29 meters. Now, does this answer make sense? Yes, it does. Because if we constrict the diameter of the hose, water is going to be flowing out of it at a higher velocity. Higher horizontal velocity means further distance traveled. So now that we've done this kind of conceptual check, we can kind of be sure that our problem is correct and be done. Thank you for watching this video, and hope to see you again.